dot.
Yes.
A belt runs on a wheel of radius 44 centimeters. During the time, the wheel takes to coast uniformly to rest from an initial speed of 1.6 rev per second. 29.5 meters of the belt length passes over the wheel. Find the deceleration of the wheel and the number of revolutions it turns while stopping.
So something like that. I may not be the best person to draw. Okay, but it's like the dot is like tight, you know? Yeah, on a wheel like that. So now, okay, let's try to identify, let's try to write down the information that we've been given. So we've been given the radius. What else have we been taught? We've been given the initial speed, revolutions per second. So the initial is what? The initial angular velocity is 1.6 revolutions per second. Then we've also been told the length is so is that linear or it's angular? 29.5 meters. Okay, so you're able to tell by the units. So 29.5 meters. Is it angular or linear? Okay, so we have to convert it. Of course, the radius has to be in meters, so it would be 0.44 meters. The displacement has to be, we want to deal with circular. So we say the conversion factor is the linear displacement is equivalent to the radius multiplied by the angular displacement. So we're able to divide by 0.44 to get what? The angular displacement in radians. Are we together? Are we together?
Yes, sir.
So I'm getting 67.04 radians. That's what I'm getting. Okay? So make sure before you get to substitute in the equations, make sure that if you want to deal with linear, make sure everything is in linear. If you want to deal with circular, make sure all the information is in circular. Okay. So now, the question is asking us to find the deceleration as well as what? As well as the number of revolutions. So in such a case, you're able to tell that they don't want your answers to be in radians, right? They don't want your answers to be in radians. So therefore, what should you do? So let's take this radians to revolutions as well. So you have 67.04 radians. So how many radians make up a revolution? In one revolution, there are 2 pi radians. So you divide. So divide into what? So that we see how many revolutions are there in there. 67.04. You're getting 10.66? Isn't that too big?
10.67.
What are you getting?
10.67.
After dividing, 2 pi.
Yes, sir.
Ah. If I put my calculator, I doubt.
10.67.
10.67? Okay. that what everyone is getting? 10.7 revolutions, right? I hope we are together. I don't want to rush because I want you guys to understand. Okay, so now, yes.
Did you get that 7.04 by multiplying the s with the radius?
So what's the conversion formula, if I may ask you? We said s is equal to what?
S is equals to the angular acceleration times the radius.
Think of s. What does s represent?
Represents the meters, the length.
Displacement.
Okay.
So the other side, it also the angular displacement. Okay. Multiplied by the radius, right?
Yes.
So you have the displacement. So now you want to find that. So you get to divide by the radius, right? Do you get it?
Yes.
So we divided by 0.44. But then looking at the question, they want our answers to be in evolutions. So we had to convert the radians to evolutions. But in a case where we've not specified, just work with the radians. Okay? And in such a case, we would have converted the initial one to radians per second by multiplying by 2 pi. And yeah, by multiplying by 2 pi. So can we move now? Can we answer the questions? Okay. Okay. I'll read the question again. A belt lands on a wheel of radius 44 centimeters. During the time the wheel takes to coast uniformly to rest from an initial speed of 1.6 revolutions per second. So what is the final angular velocity? It's what? It is stopping. So the final is what? Are we together? Are we together? Are we together?
Yes, sir.
Okay. Okay. So now we are able to see the information that we have. In summary, what we have is this. We have our final angular velocity, we have our initial, we have our displacement, we have our radius. So now, which equation can help us find acceleration? So we are trying to use an equation that doesn't have what? Time. Because we've not been given the time. So, like I said, I don't want you to master your formulas. So therefore, the formula that you can go for is this one. Go for this formula. Of course, you know, it doesn't have what? It doesn't have time. Then you ask yourself, where there is V, I can put omega. Like that. Know the counterparts. Are we together?
Yes, sir.
I can love this part. So what are we trying to find? Acceleration, right? We can make it the sum. Okay, we can substitute. The final is 0. The initial was 1.6. So squared. We don't know the alpha. That's what we're trying to find. The angular displacement was 10.67. Okay. So this one comes the other side to be negative 1.6 squared equal to 2 alpha 10.67. So we divide by 2 by 10.67, 2 10.67. So if your answer doesn't come out, then there's a mistake somewhere. Divide and see what you're getting. So what you're finding in this case is we are finding the angular acceleration. What are we getting?
0.1199.
Is it negative or positive?
Negative.
So what will be the units? What will be the units there? Think of what you've been using. Lads per second squared. Are you sure? Have we been using lads?
Or revolution per second squared.
So what matches up with the answer in the given there, right? So I hope we've understood the process. Okay. If we are done, when we are done, try to check through at your own time. You'll be able to connect. Okay. So now let me now answer the other question, which says the one that you're asking about, the number of revolutions it turns while stopping. You're now trying to determine the number of revolutions that's going to turn before stopping. What do you do? Didn't you already answer that question? We answered it, right?
I think we were
Yeah, we answered it. Because it's this. Just convert this to revolutions. First convert to radians. Then from radians you get to what? To revolutions. So we answered it at this point. 10.6 revolutions. Okay. What else? The second question, I believe we answered it as well. From you're able to answer it. This is why you equate mv squared over the radius should be equal to mu k multiplied by the. So this is the part where we are saying that the roundabout mv squared over radius should be equal to mu k multiplied by what? Mg. So it will be m will cancel out, you have v squared over r being equal to mu kg. You want to find mu k, it will be mu k is equal to v squared over r multiplied by gravity. I believe that is okay. So I say, just like I said, they can ask you to find the velocity if they've given you the coefficient of friction, or they can ask you to find the coefficient of friction when you are given the velocity, just like in this case. Okay. So be careful. That v there represents linear velocity, so no need of you converting it. Just use it as it has been given. Okay. Are we together? Are we together, guys?
Yes.
Okay. What if I change that part? I say Okay. Okay, so all these are counterparts. Even here under rotational motion, we have work, energy, power, momentum, and everything else. It is also under this part. We also have it. Okay? So how then can we understand this part? Okay? I want you guys to understand things like force, mass. What else do you want to talk about? I think these are the two important things. Then I also need to talk about the kinetic energy, and momentum. Then I believe we'll be done for tonight. Okay. So force. How do you calculate force? Force is equal to what? MA. Right? Are we together?
Yes, sir.
What is the counterpart of force under rotational motion? What causes motion under rotation? It's what? What is the counterpart of force? You guys. Anything turning. What causes the turning effect?
Torque,
Pardon?
torque.
Yeah. Thank you. So what's the counterpart? Okay. Starts with a door. Okay. So from the point where you're applying a force to a point of, let's say, the hinges or the pivot, we can call that to be the radius, and that's to be our force. So torque we know is given by product of what? Force, radius, and what? Sine the angle, right? The angle made between the force and the pivot of the hinges. Okay. So usually we want to determine torque where it is 90 like this. Okay. When it's 90, when it's perpendicular there, the formula will just reduce the product of force and radius. Okay. So we already know that. So now, what is the counterpart of mass under rotational motion? Rotating objects possesses what do we call that? The mass that it possesses. Rotating objects.
Moment of inertia.
Yeah. Okay. It's a moment of inertia. Denoted by what?
Greater.
Capital letter I. Okay. Kinetic energy is C. mv squared over what? Over 2. So the mass is moment of inertia. So now, when you look at the formula for force, force is equal to ma. So we know the counterpart is torque. So we can therefore say that torque is actually equivalent to mass. What is the equivalence of what's the counterpart of mass? It's moment of inertia. What is the counterpart of angular acceleration? It's supposed to be torque. Okay. What's the counterpart of acceleration under rotation? It's angular acceleration. So what is the other formula that you need to know as you talk about angular acceleration? Or as you talk about the torque? Torque is also a product of moment of inertia and what? And the angular acceleration. And you need not to worry about the moment of inertia. They are always going to give you in a question the moment of inertia of a given rotating object. If it's a wheel, for example, we already know that it's what? It's r squared. If it's a disk, it's half mr squared. You'll be told. Okay. I move. Momentum. Momentum we know is the product of what? Mass and what? Mass and velocity. So rotational momentum is what is the counterpart of mass? Sylvia. Then velocity.
Angular.
So that's how you determine rotational momentum. It's moment of inertia multiplied by the angular velocity. Okay. Another formula, kinetic energy. Rotational kinetic energy is determined by where there is mass, we can put moment of inertia. Where there is velocity, angular velocity. Where there is a 2, it remains a 2. Okay. So guys, you don't have to master the formulas under rotation. Just know the counterparts. Okay? Know the counterparts, then begin to substitute. Okay? That will make your work easier. Practice, practice, practice. Okay. Let's get to do at least 2 questions. The other questions, you try them out. Then I'll review the solutions. From what we've covered, I feel it's enough and it can help us answer a lot of questions. So let's try to answer some of the selected questions, especially the one under conservation of rotational kinetic energy. This question, I'm sharing the screen. Is it showing on that side? Are you able to see that I'm sharing the screen? Are you able to see? Hello?
Yes, sir.
Okay. So, conservation of energy under rotation. When you have something there like a ball rotating, okay. So as it gets to the bottom there, at that point initially before starting to move, it is possessing what energy? Potential energy, right? Then as it begins to move, somewhere there it will possess potential plus kinetic energy and rotational kinetic energy. Okay. Then at the last point there will just be kinetic energy and what? Rotational kinetic energy. Okay. So kinetic energy is not converted from linear to translation. To just possess both linear and what? Rotation. Are you getting me? Okay. So if we are to answer the given question there, what are they saying? What is its linear speed when it reaches a point 50 centimeters vertically lower than its starting point? So consider the point, the 50 centimeters there to be the ground. Okay. So 50 centimeters converted to meters, that would be 0.5. Okay. The radius of the hoop has been taught to 0.06 meters. Okay. Are we together? So now, initially we know that at that point it is possessing potential energy. So we have potential energy. It is being converted to what? As it reaches the ground there, it is converted to kinetic energy and rotational kinetic energy. Okay. So potential energy, we all know that it's mgh. The linear kinetic energy is mv squared over what? Over 2. Then kinetic energy rotational. What are the counterparts? It's the moment of inertia. The velocity is angular. Then over 2 as well. So we can make the equation to look easier by multiplying by 2 throughout. Okay. Even before we multiply by 2, we've been told the moment of inertia of the hoop is mr squared. So where there's I there, we can put that. So I have mgh equal to mv squared over 2 plus mr squared, then omega squared over 2. So from this point, we're able to see that the mass is common, right? And you can therefore divide. Okay. And then multiply by 2. So when you multiply by 2, this side you have 2gh. There you're remaining with v squared plus r squared omega squared over, the 2 has already gone because we are multiplied by 2. So here it's divided, and there it is 2gh. Okay, so the question is asking us to find the linear speed. So we don't want to see omega there, but we know that linear speed or velocity is equal to radius multiplied by omega. So if you make omega to be a subject, it is v over what? The radius. So therefore, where it's going to be 2gh v squared plus r squared. Where there is omega, it will be v over r squared. So you're able to see that the radius is able to cancel out. Then you are going to have 2gh being equal to v squared plus v squared. You have 2gh is equal to 2v squared. Okay. From there, you're able to divide by 2, and you're able to find your what? You're able to find your v as actually the square root of gravity and what? Height. Are there any questions, guys? Are there any questions? So what is important is for you guys to understand that at the highest point, the ball possesses potential energy. Then as it gets to move down, to possess kinetic energy and rotational kinetic energy. Okay. Then in a case where we've asked you how fast it is going to be rotating, where there is v there, you put this. So what you find what? The rotational speed. I'll allow any questions. I'll allow questions.
Oh,
There are no questions.
I have.
Okay, what's the question?
Since the hoop it does not reach the ground, it is just somewhere there. Is all potential energy converted to kinetic energy and kinetic rotation? Why have we not included?
Okay, good question. So the reason why we've not included the what the potential energy at that point is because we've not been told this part, like how high it is, because we can't predict. So if at all we were told the height from that point to this point, we would have predicted the potential energy from this point to that point. Like we use that height, then now for this one we can now use the height going down. But in this case we've not been taught. That's why we're taking assumption to say this is the ground. And remember, the height that we're putting into consideration is this one. So it's only this energy being lost. Meaning that all of this potential energy at this point has been converted to what? All of this potential energy at this point. But if at all we had the potential from this point to that point, us saying that it has all been converted to this would have been wrong. But in this case, we've seen that this all height has been moved to 0. So all this potential energy has been converted to this. But if at all it was down here, us saying that it has been converted to kinetic energy at that point would be wrong. I don't know if it makes sense.
Thank you, sir.
Hello? Are we together? Okay. Let's answer this one to be the last question for tonight. I know most of people kind of struggle with this question. Are you able to see the question that I've shared? People are already tired. Hello? Have you seen the question that I've shared?
Yes, sir.
Okay. You can read the question for us, Sylvia.
A wheel of radius 6 centimeters is mounted so as to rotate about a horizontal axis brought through its center. A string of negligible mass wrapped around its circumference carries a mass of 200 grams attached to its free end. When allowed to fall, the descent through 100 centimeters is 5 seconds. Calculate its moment of inertia and the tension in the cord.
Okay. So as usual, we try to correct the data. Okay. So a wheel of radius. So we've been told the radius is 6 centimeters. So you can even be converting direct to meters. You divide by 100, 0.06 meters. So it is mounted as to rotate about the horizontal axis. A string of negligible mass wrapped around this circumference carries a mass of, so the mass attached is 200 grams, which is 0.2 kgs. When allowed to fall, it descends 100 centimeters in 5 seconds. So we've been given the displacement. 100 centimeters to meters, that's 1 meter. The time has been given to be 5 seconds. Okay. What is the first question saying? The first question is asking us to find the moment of inertia and also the tension in the cord. Okay. So if you guys are able to remember, what did we say? we said force is equal to ma. Now here we talked about torque as a counterpart of rotational motion. So torque, we said mass is moment of inertia. The acceleration is angular acceleration. So meaning that if we are able to find the torque and the angular acceleration, we are able to find what? The moment of inertia. Okay. So how are we going to find the torque? So we're going to find the torque by first of all finding the tension acting in this rope. So if we find the tension is a force. Okay? The tension is a force. So how do you convert force to a torque? You multiply torque. Yeah. So how do you convert force is equivalent to what? Force is actually equivalent to torque multiplied by the radius. Like we said, linear velocity is equal to radius multiplied by the angular velocity. So the same applies here. So where there's a torque where we can put force, actually you can say, what are we saying? What am I saying? Okay, let me not confuse you guys. Okay, so this is what we are saying actually. We said torque is actually equal to force multiplied by the radius, if you can remember, you guys. Alright? That's what we said. Torque is actually equal to force multiplied by the radius. But you also understand that tension is actually equal to what? To a force. Okay. So I'll put torque there. So torque is actually also equal to the tension multiplied by the radius. Okay. So we're able to find the moment of inertia. Are we okay with the analysis made so far? So whenever you're given something like tide, yeah, with a, like providing a support like that, it is always, whenever they ask for the moment of inertia, you need to divide the torque divided by the angular acceleration. Okay. And where you know torque is actually the product of tension and the radius over angular acceleration. So now it is a matter of you finding tension and angular acceleration. So from this given information here, we're able to find the acceleration. Okay. Now let's first of all try to find what is more involving, which is determining the tension. Can we do that? Okay. Hello. Can we do that? Okay, people already died. Okay. So now, what is putting this down is actually the weight, which is mg. Okay. So for it to accelerate downwards, it tells you that the weight is actually greater than what? The weight is actually greater than the tension. So the net force is mg minus what? Tension, implying that the weight is bigger. It is the one that is causing an acceleration. So we make tension to be the subject. Tension is equal to mg minus ma. You know your gravity, you know your masses, but you don't know your acceleration. Okay. You go to your equations. You've been given the time there. You've been given the time. So how can you find the acceleration? How can you find the acceleration? You can go to this equation. S is equal to ut plus half at squared. the distance is 1, the initial was 0, okay? Initially it wasn't moving, so when it started moving, so you have half, the acceleration you don't know, the time you know it's 5 squared. Okay, so you have 25 divided by 2, 12.5, divide that into a 1. So you find that your acceleration is what? 0.08 meters per second squared. Okay? Is that what you are finding? So from there, you're able to find the tension. You factor out the mass, 0.2. Gravity is 9.8. Acceleration is 0.08. Our tension is 1.944 newtons. Okay, so we found the tension in the court. So you can substitute. The radius is 0.06. The angular acceleration. So we found the linear acceleration. So we divide by, remember we said A is equal to radius multiplied by the angular acceleration. Anything in linear can be converted to circular by multiplying by the radius. Okay. So from there, for you to find the angular, you divide by the radius. So you have 0.008 divided by 0.06. We find 1.333 radians per second squared. So from there, you have 1.944 multiplied by 0.06 divided by that. So I'm finding 0.08748 kilograms meter squared. Any questions? Any questions? Are there any questions? Are there any questions, guys? Okay, so I hope the class reminded you of the concepts that you already know, and we hope this will help you as you approach exams. Okay, so I have another class over the weekend. We'll look at thermodynamics. Okay, so if you guys still have questions, share them to the group. If you still can't answer some questions for under projector and rotational motion, you can let me know.
Actually, there was a class being recorded.
Yes, I recorded. I've recorded the part from the concepts I didn't record, but I've recorded the questions. Yes, I recorded. Okay. So, good night.